This is Structural Analyze and Modeling Portal section Truss Analyze GSA tutorial part. For this tutorial, you should be able to learn how to build a simple truss model in GSA. For better understanding, a truss is provided as an example shown in Figure 5 in the GSA tutorial, like that, whereas the other corresponding data has been provided from Table 4 to Table 8 at the end of the GSA tutorial handout. You should know that the example truss and the cross-section of the members in the tutorial handout are different from those given in the Truss Analyze individual assignment. So that to begin with, let's first create a new file and populate relevant info. So in our case, that would be structural analyze and modeling portal. So subtitle we can name it as truss analyze, and then click on next. So the structure type we choose plan instead of space. Units we use kilonewton-meter, and beware of the unit of length small, and stress, especially if you are not quite sure about the unit of Newton per square millimeter to Pascal or kilopascal, megapascal, gigapascal. You can always select the one you want. So in our case, we still use the Newton per square millimeter, and then we can finish. We don't need to specify the others. And else, whether you need the grade, and you can click on no. So after we get to this main window, the graphic view, the next thing we should do is to go to the gateway menu, click on knot coordinates, and specify the knot details according to table 4 in the GSA handout. So that will be port knot 1, that's 0, 0. Port knot 2, there's 5, 0. Port knot 3, 10, 0. Knot 5, 15, 0. Knot 4, 15, 0. And knot 5 is 10, 5. Knot 6, that's 5 and 5. So let's have a look. Oh, we don't need to define knot 7. Yep, so we can delete. So we can click on label knot dots and label knot number. Oh, it seems we defined something wrong. Oh yeah, here should be 5 and 5. Yeah, so we have defined the knots arrangement, which is similar to the truss in Figure 5. Then we need to create the elements between these knots. So by click on the Add Elements gap tool, link 1 to 2 these knots we defined. Of course, this doesn't link them randomly. We link them according to Figure 5. Okay, like that. So yeah, the same as this one, right? Okay, so the next step we should do is to select them all, which is click on select element members from the left hand side, or press E on your keyboard, and right click to use modify select element, or just click the here modify selection tools from the left hand toolbar, and modify type of the element to bar, then press OK. The reasons for this are because bar elements only carry tension and compression, so there will be no shear forces or bending moments. Meanwhile, this action effectively makes all joints free to rotate or pin as intended for our problem. So the next step we should do is to generate support, which is go to the gateway menu, the knots, and restraint. So according to table 5, yep, in the GSA handout, we should restrain the not 1, x and y, s and z direction, as well as not d, the z direction. Okay, then we go to graphic view, we click on the label restraint. You can see that not 1 is pink and not 4 is restrained in z direction. Okay, then we should define the load cases, which is go to the gateway menu, cases and tasks, and load case specification. Yeah, select the first one, which you can click on the wizard 2 on the toolbar at the top toolbar, or you can right click, select wizard, and give it a name. In our case, the point load. Type we can leave it undefined, the others is can leave it undefined. Then we need to create the nodal loads. So to do that, there are actually two different ways. The first one is go to the gateway menu, go to the loading, and go to nodal loading, not nodes, and select the first line as wizard. So give it a name as point load. For the node list, according to table 6 in the handout, that would be 2 and 3. Locus is locus 1, direction is z, value that will be -10 kilonewton. Okay, then we go to graphic view. We can close all this and turn on here all load diagrams to check the loads whether it has been added correctly. So yeah, we can see there's two loads. Apply on these two knots. Apply on knot 2 and knot 3. And if you want to have a look at value, so click on select for animations and select these two knots. So you can see that there's a 10 kilonewton force applied on here and 10 kilonewton point for load applied on here. Okay. So then there's another way to do that, which is, for example, go to the left toolbar menus, click on select nodals. So select knot 2 and knot 3, and right click, create nodal loadings, and create node load. So right then it has already input the node list. So sometimes when you need to select call of nodes and to apply loads on them, it's a better way to do that because you don't need to input the node number by yourself. So again, name as point load. Load case, there will be case 1, direction is z, and the value is -10. So we still have the same load case arrangement. Okay, then we should define the cross-section properties, which is go to the gateway menu, properties, and before we check we define the cross-section property, it's also important to check the material property. So here we go to the standard, because we need to use steel material later, so it's very important to check whether the Young's modulus in here is the same as specified in the table 7 of the GSA tutorial handout. So that will be 2.05 E plus 0.5, same as in here. So that if it's not, you need to define the materials. For example, input the name here, select the steel, and change the elastic modulus. Sometimes when you deal with the concrete project, you usually need to redefine them because steel is the Young's modulus for different grade of steel is quite constant, but not the same thing for concrete. Okay, so then we can define cross sections, which is go to the section properties, select the first lines, use wizard. So we can populate a name for it, which is the Truss member. Yep, and material is steel, as we just checked. The cross-section type is rectangular and need to be whole sections. So that for the property, there will be 500 in depth, 500 in Y. Thickness is 25 and 25. Okay, go to next and finish. Okay, then we need to go to graphic view and close these two, turn on the section display and rotate it. Okay, to conduct the visual check. So it's the same as here in figure 5 of the GSA tutorial handout. Okay, then we can close it and go to the Y elevation. Okay, so everything is done for the input. We can start to analyze it by clicking on Analyze All from the top toolbar. And it's quite quick, so we can. Then we need to check the SEO load diagram. So click on the FX SEO load diagram. So you can see the load diagram looks like that. And in order to know the actual value, you should use select for animation on the left hand side or press A on your keyboard and select all the loads so you can see the loading. Sometimes what you see here may end up like this because it uses a different kind of numerical format. You can change it to engineering or decimal like that. Okay. If you think the diagram is not obvious enough, you can increase the size by click double size of diagrams. If you think that's too big, you can half the size of diagram, okay, or you can rescale them. Then we need to check the support reactions, which is click on the FX, FY, and FZ reaction diagrams. So you can see there are two force around here. So we can select them to see its value, which is 10 kN to 10 kN right on node 1 and node 4 in the Z direction, upward. Okay, so that will be all for the GSA tutorial part of the section Truss Analyze.